Okay, so welcome back. So for today's tutorial, I just figured out I would go through some very useful so-called isomorphism. And then I have another little thing prepared for after that, but that's not gonna take long. So maybe, I don't know, 15 to 20 minutes. I think it's more useful if I just share this with you, and then if you want to go through the computations, you just do yourself, because it's a little bit absurd to now do them here all together, I think. Something that's very useful in quantum information, and I don't know if this holds in infinite dimensions or so, you will certainly know much more than me here, is something with a very scary name. The Coves isomorphism, as I just learned, I'm supposed to pronounce it. But actually very, very useful and really not that complicated. So the essence is to realize that because linear maps say from matrices to matrices, so as in like the superoperators that we were seeing yesterday that represent quantum channels, because they themselves can be expressed as a matrix in this kind of composite vector space. So that, let's say, this set or vector space is isomorphic to this one, which is isomorphic to this one. Because of that, notions of positivity for the superoperators, so for the linear maps, correspond to or are isomorphic to notions of positivity on matrices. The most famous one is the fact that a completely positive linear map is isomorphic to a positive semi-definite matrix. So that's wonderful. You can do that's very, very useful. Yeah. So a little more specifically, so consider a linear map, say, from the set of Hermitian matrices of size d times d to itself. I believe that can be done with a different dimension in the outgoing set than the arrival set, but I figured it's simpler if we just take here the same dimensions. And we were calling it like epsilon yesterday, or this calligraphic E, actually. Okay, then define its Choi matrix. I don't know why Gemma it's not there, but I think that's usually called the Choi matrix, as 1 over d squared times, or like this map tensor, the identity map, applied to the maximally, so the projection onto the maximally entangled state. Okay, so if d would equal 2, that would be the projector onto the phi plus state that we saw many times yesterday. Remember, like 0, 0 plus 1, 1, and then the bra. Okay, so this is a generalization, let's say, to d dimensions, and the 1 over d squared. Now I'm a bit confused about why it's d squared instead of just d, because with phi plus we have 1 over square root of d, so we may just have 1 over d, okay? But the idea is that this completely positive, or this linear map is applied to only the first half of the this maximally entangled state, and the second half, so nothing happens on the second half, or rather just like the matrix elements I and j are there to keep track of what's going on in the first half, something like that. And then we have the following equivalences. So if we have, so on the one hand we have a linear map, our curly E, from mat D to mat D, so complex matrices to complex matrices. Or here I was taking Hermitian, but it doesn't matter. On the other hand, we have this matrix C sub curly E, which is this Choi matrix defined here. This is a matrix itself. And then the statement is that this calligraphic E is completely positive as a linear map if and only if this C of epsilon is positive semi-definite as a matrix. And similarly, this calligraphic E is a positive map, which means that it maps positive semi-definite matrices to positive semi-definite matrices, but no requirement on how its extensions with the identity behave. If and only if this Choi matrix is block positive, which is something weaker than being positive semi-definite. I will define it in a second, but it means that under contractions with elementary tensors, it is positive, but the result is a non-negative number. But if you contract it with a vector, which cannot be expressed as an elementary tensor, the result could be negative. Then this linear map is so-called entanglement breaking, which I will also define in a second, if and only if the corresponding matrix is separable. And entanglement breaking means that for any positive semi-definite matrix that is input into the map, the result is a separable matrix. So it breaks any entanglement that the input might have. And that's like a little corollary. If the map is completely co-positive, which means that it is completely positive followed by a transposition, then the corresponding Choi matrix has a positive partial transpose. And so I wrote down here every step a little more carefully in case anyone wants to kind of go through the little go through the equivalencies and do the exercises of seeing that that is the case. Well, this is what I just said for the first equivalence. Maybe the other interesting thing to remark is that by walking through these equivalents, one sees that the Krauss decomposition of the completely positive map is essentially the same as the expression of a positive semi-definite matrix as A dagger A. So those A's, after shuffling some rows for columns and so on, they become these Krauss operators of the completely positive map when you write sum over AK dagger. And note, by the way, that if curly E is a quantum channel, which means that it's not only completely positive but also trace preserving, the condition of being trace preserving translates to a somewhat weird or not very natural condition, normalization condition on the Choi matrix, as in some normalization on the left side or something like that, or that if you contract the left side and it's normalized. So it's only complete positivity that's very naturally mapped to positive semi-definiteness, but being a quantum channel itself corresponds to a sort of weird positive semi-definite matrix. Okay, on the other hand, yes, this E is a positive map if and only if CE is block positive, which means what I tried to express earlier, namely that if you contract it with, you have here V and W, for any V and W that is non-negative, it suffices to take such rank 1 projectors in the definition of positivity, right? I could also have said the trace of X tensor Y times C epsilon is non-negative for any positive semi-definite X and Y, but that would be equivalent to that because such rank 1 projectors are kind of at the boundary, and they suffice for that. Yeah, and then the other one, that's also easy to see. So E is entanglement breaking. That is to say that the outcome E on rho is a separable matrix for every positive semi-definite rho. That is to say, E, and so E can be expressed as that. Let's say as a convex combination. So a sum over K of some positive, so a positive semi-definite matrix sigma K times the trace of tau K applied to rho. So tau K times rho is something. Doesn't matter what it is. It's not even Hermitian generally, but the trace of the product of two positive semi-definite matrices is a non-negative number, and then the result, is that. If and only if, is that?
So do you mean that the epsilon tensor identity maps into separate? Because like epsilon is mapped from MD to MD, so like
yeah, something's fishy here, right?
It can't be separable, right? Probably epsilon tensor identity maps everything to.
Something is wrong, right?
To separable matrices. That would make sense. I'm not sure if that's the case.
For the moment, we don't have MD is not does not have.
Yeah, there is no notion of separability.
I think I am missing something. Okay, so something is wrong here. Yeah, what? Sorry?
For the condition for entanglement breaking, it's E of rho, it's then tensor E of rho is
Tensor with identity.
Okay. Okay. I'm not sure. So I worked this out this morning, and I made it worse. I shouldn't have done it. Because what I remembered was that these sigmas and these taus were essentially the sigmas and the taus in the separable decomposition of C sub epsilon. So, but there's some tensor product missing. Yeah. Okay, so I will correct that before.
That piece is okay. It's just the line above.
Definition is.
The line above doesn't quite make sense.
This one.
Yes. Not like.
Yeah, I agree.
Formula is okay.
So this should be E tensor ID.
Yeah, I think so. Because like in Clay matrix, you apply epsilon tensor identity to this, to this maximally entangled thing, so it's separable. You write the decomposition and then get the formula.
Okay, I'm not convinced, but can I think about it later?
Yeah, sure.
Okay, but this is true, right? This is true. Okay, and finally, E is completely copositive. That is to say, completely positive followed by a transposition if and only if the Choi matrix is a matrix with a positive partial transpose. That is to say, positive semi-definite after transposing the first subsystem. I hope I got that right. I hope it's the first indeed. And this is a figure from the PhD thesis of Jutta van der Eyden, which I found quite nice. That says that because every kind of one point over here, as in a linear map with some positivity property, corresponds to a matrix with another positivity property that is in correspondence via this isomorphism, then also the cones of such linear maps are in correspondence with some cones of certain notions of positivity on the matrices, and more particularly, so this is the famous one again, that the set of CP maps corresponds to the set of PSD matrices. But we also have that the set of, let me follow the same order. Number 2, yeah, that's a big one. The set of positive maps corresponds to the set of log positive matrices. the set of entanglement breaking maps to the set of separable matrices and the set of OCP maps to the set of APT matrices. It's a tool that appears kind of all the time in quantum information. It's good to know. Do you have such a thing in dimensions?
Question. So about the separability matrices beyond the definition, so physically what I'm supposed to think of these, so like if I say apply it to a fully entangled space, does it give me a non-entangled state too?
Is that a question about what is a separable matrix, or is the question what is an entanglement breaking map?
Yes.
Okay. Yeah, so it's supposed to always result in a separable state to break entanglement for any input state. And if you input something that's not positive semi-definite, it may do something else. Okay. Then I had prepared that other little comment exercise. Yeah.
So question still to the first one. So this correspondence, I mean, does it, if you compose two maps,
Yeah.
does it do
Not
anything
nice.
nice? No.
Not nice. Unfortunately. Yeah.
So isn't like correspondence for trace preservation as well? Because quantum channels preserve trace.
Yeah, it's what I tried to say earlier. If they preserve the trace, it means that it's like that the dual is unital. Maybe that's easier to see. So if you compose it with the identity on one side, it gives the identity. So actually, for the positive semi-definite matrix, it translates to a weird normalization on one side. It's not very natural. The trace condition, so that the linear map be trace preserving, does not translate to a very natural condition on positive semi-definite matrices. For example, it does not translate to the fact that it be trace one, that the positive semi-definite matrix is normalized. But maybe if it's both trace preserving and unital, it does.
I think it is both just in the unital chance. Then both partial traces of the true matrix are the identity.
Yeah. Yeah. And by the way, also, if you represent such a map that's a very kind of bipartite correspondence. If you represent the map as a tensor network, yesterday we talked about tensor categories, it's very natural to see, because as a tensor network, a map is a box with 4 legs, and say that the linear map kind of acts from bottom to top. Excuse me. Say that it maps from left to right. Then the corresponding positive semi-definite matrix acts from bottom to top. So with a tensor network, you just kind of say, or what you change is the designation of which legs are in and out. So maybe that's helpful. I can write that down. So say, I will start here. As a bipartite positive semi-definite matrix is like, so these are like, say, rows and columns. But the CP map is like the same object, but you're seeing that it goes like from right to left. So, and in between there is this Choizami-Olkowski isomorphism. So what it does is, these 2 legs are doing the same thing, but these have been flipped. So this is now an outgoing leg, and this is an incoming leg. This is the idea of what this isomorphism is doing. It's doing a funny shuffle of rows and columns. And also here you can immediately see that if this is of the form A dagger A, this is of the form A dagger A. Yeah, I could write it down, but it's quite nice. Yeah.
Is there a condition for true matrix that
Sorry, automorphism?
Yeah, so simply after the formula x goes to ux is
one cross operator, so there is a cross operator.
Okay, right. So the Krauss rank of the map corresponds to the rank of the PSD matrix. Yeah. Okay, so as a final comment and to, I don't know, get like maybe a new angle, shine some other light, even if shortly, on some properties of quantum channels, you can talk about things like eigenvalues of the quantum channel. If you care about that, there's a lot of valuable results in the unpublished notes of Michael Wolf online that he put up there in his website, I don't know, about 14 years ago or something, and haven't been touched ever since, but that's the best source I know. And so maybe one surprising fact is that the eigenvalues of a quantum channel can be complex, but if they are complex, then they need to come with a complex conjugate pair because it's a hermiticity preserving map. But they can also be negative. As maybe the simplest example, which contains quite a lot of interesting things, you can consider this qubit channel. So this is, you have to imagine that rho is a qubit, or rho is describing the state of a qubit. That is to say, it is a 2x2 matrix, positive semi-definite of trace 1. And such a matrix is mapped to 1/3 of the trace of rho times the identity matrix of size 2 plus the transpose of rho. So here you can immediately see that. So this is a convex combination.
You have the transpose here.
Yes?
So that's not completely positive.
Yeah, thanks for the comment. But in
you call this quantum channel evidence.
Excuse me? So this is a convex combination of a map that is not completely positive, namely the transpose, with another map that is as dirty as it gets, right? Remember, it's the completely depolarizing map, the one that introduces as much noise as possible. And the combination is in some sense maximal in the sense that it is the maximal amount of the transpose that you can have in that combination, in that convex combination, so that the overall transformation is still completely positive. It's not immediate to see from here, but it is.
If I can make a comment, but actually this is excellent for the exercise session because the matrices that Mateusz wrote half an hour ago, plus Choi-Jamiankowski, will allow you to show very quickly what Jeff just said if you want to convince yourself that this thing is possible.
Okay. So and from this expression, first of all, we can check that it's trace preserving. Well, if you take the trace of E of rho, it's 1/3 times the trace of rho times 2 plus the trace of rho. So it's just the trace of rho. That's good. But it's also not obvious that it's completely positive. I mean, what I would do would be to try to find the Krauss operators. It turns out you can do so because it is. But I was trying to illustrate the fact that the eigenvalues can be negative. And in this case, so the eigenvalue 1 is always there for a quantum channel, just like it is for a stochastic matrix. And it can be degenerate. And if it is not degenerate, you can still have eigenvalues at the so-called peripheral spectrum, that is to say, of modulus 1. If you have these eigenvalues of modulus 1, there's a lot of structure there. They need to be like a root of unity that is like of the form e to the I 2 pi j over r, where r is at most d or d squared, where d is the size of the incoming matrix, and then for all such j, so all of them need to be there. And you also know stuff about the corresponding eigenvectors. So let's say the peripheral spectrum is very strongly constrained, but if it's not of modulus 1, they can be anything. In this case, we have 4 eigenvalues. 1 is always there, right? 1/3 minus 1/3 and 1/3. And it turns out that in this case, the eigenvectors are the Pauli matrices. So again, that illustrates why you can have a negative eigenvalue, because the incoming matrix need not be positive semi-definite, like y. So it can be mapped to something negative. It's not in contradiction with a map being completely positive. And it's immediate to check that these are the eigenoperators in this case, because, well, the Pauli matrices have 0 trace. So all of them get killed in the first term, and y is equal to minus its transpose. So there you go. You can also, there's a similar map that has eigenvalues 1 minus 1/3 minus 1/3 minus 1/3. So you can really, and well, from the fact that you can talk about the determinants of such maps. And for quantum, so that's something that Michael Wolf and Ignatius Dirac did some years ago in a very nice paper called Dividing Quantum Channels. And and there's a certain range where they can be, these determinants. And in this case, for quantum channels, it turns out that the minimal determinant that a quantum channel can have is minus 1/27, which is precisely this. And from this fact, you can conclude something quite interesting, I think also physically, which is that this quantum channel cannot be divided, not even a single time. That is to say, into 2 equal channels. So you cannot take a square root of this quantum channel that is also a quantum channel. None of the square roots works. You know, there are several square roots because for each eigenvalue, you have different possibilities. But the only square roots, or the only splittings are trivial, are like of the form U dagger, and then the very same map. So, and there, in fact, there's a whole analysis on which quantum channels can be divided. And I think that, as I said, also interesting conceptually, because they describe an evolution that is in some sense discrete and not continuous. It cannot be sliced down into smaller pieces, in contrast to other evolutions in physics, which are continuous in time, and you can take some limit to 0, and things are supposed to be trivial in the limit. In this case, you cannot even slice it once. Yeah, and just as a comment, if you do such analysis of quantum channels, it can be quite ugly, because you need to represent, or you can analyze its eigenvalues by representing the quantum channel as a matrix. But doing so is doing a notable amount of violence to that object, because if you see it as a linear map from matrices to matrices, it has wonderful properties, as in it's a completely positive map, it has the cross representation and so on. But when you represent it as a matrix, it need not even be diagonalizable. So it has Jordan normal form. Yeah, you can say some things about the spectrum and all. You can have 0 eigenvalues, and so on.
Right, you could take odd roots in this case, like the 3rd root, and the 5th root, and the 7th root of this quantum channel. It's just a problem with even roots.
I don't think you can.
It's minimality of the determinants. This would be a problem.
Yes. Minimality, yes, of the determinant. So maybe also in physics, the continuous quantum channels, I should have said that, are of the form e to the TL. And L is called the Liouvillean of Lindblad form. Sometimes it is time independent, sometimes it is time dependent, in which case you need to integrate over t in the exponent. These are continuous in time, right? If you take the limit t to 0, you get the identity. But there are other classes of divisibility, and this is kind of the worst. This can be generalized to the dimensions as well.
Is there this kind of minimality of determinant in higher dimensions also?
Yeah. You can find it in the paper by Wolf. You can write a similar expression of the quantum channel, kind of the maximum amount of transpose that you can put in combination with this completely polarizing map so that it's still completely positive. Mm-hmm.
So I feel like you can say it, it's just not very interesting. Right? Like if you have a trace preserving map, then the Choi matrix, like all the blocks should just have a trace. So that you end up getting it. When you take the partial trace, you get the identity matrix.
Yeah, when you do the partial trace of the Choi matrix, you get the identity.
Yeah, so I think that's kind of all you can say.
Yeah. But my complaint was that it's not a natural condition on the PSD matrix.
Okay.